Well, this room is actually sponsored by OpenSUSE. So
Close enough.
actually, it's pretty cool. It's like they're actually got a really cool booth downstairs. I don't know if you've seen them yet. OpenSUSE Open Build Services offers powerful team and project collaboration features for forking of packages and merge requests. OBS build, RPM and TGZs for ARM v5, v7, v8, and x86 and more for 28 Linux distros. Pull code directly from Git or SVN and build each package in a fresh VM with OpenSUSE OBS. So the OpenSUSE guys, the expo floor is open till 2. So after this, you've got about a half an hour before the next session to go check it out. By the way, Subash is over here. If you guys turn around, Subash, wave your hand. He helps run the big data groups here in the LA area. We've got a flyer in the back for the big data groups. Join one of those. We're going to do a big data camp. This is going to be year number 3, June 27th? June 27th. So, if you want to learn more big data, we're always looking for more presenters also. And with that, Matt Davis, who actually, as I said, Matt, you want to do talks for our big data group, talk to Subash, man. We'd love to have you.
Okay,
thanks.
Cool. Is this thing working? Can you hear me okay? All right, awesome. Yes, as you said, my name is Matt Davis. I work at OpenX. We had a booth downstairs as well. I don't think we have it open today, though, right? No. Okay. So you missed out if you didn't get to it. So what I'm going to be talking about today has to do with distributed databases. We use a lot of distributed data at OpenX. We have distributed databases. We also have distributed file systems. If you're familiar with Hadoop infrastructure, we do a lot of that. We have distributed columnar stores like Vertica. Get to that in a little bit. But I want to talk about the word measure. What is a measure? A lot of people see this and they think, oh, well, there's one right there. That's a measure, isn't it? It is. It is a measure. But a measure is a little bit more than just sections of a musical composition. Measures are rules. They're something that actually measure. It's hard to say measure a quantity without saying measure, but a measure is a quantity of a substance. It's a unit of time, which is more like the musical measure. And it's the capacity of something, the measure of something. So these different definitions of measure all work with the way that we actually view our distributed systems. We're always trying to figure out what's going on under the hood. We're always trying to get a feeling for what's happening with our distributed systems, especially distributed databases. And the word measure is something that I really like to go back to when I like talking about distributed systems and when I like figuring out distributed systems and figuring out the problems. So let's go back to that measure before. John Cage, probably not something you would expect to hear at a distributed systems talk or even a conference about Linux. I don't think John Cage ever even knew what Unix was. But John Cage worked a lot with measure. He worked a lot with structure, and he worked a lot with rhythmic structure. A lot of composers at the time were doing harmonic structure, melodies, chords, those kinds of things. John Cage wasn't that cool with all that. He wanted to find a different way to approach a composition. So he looked at the rhythmic structure of a composition. This is just an example of one of his pieces. That's the, that's the section of measures that we saw in a couple slides ago. And that's the rhythmic structure breakout of that measure. Actually, just the first part of the piece. You can see it's very mathematical, it's very methodical. It's very much what Cage liked to call a macrocosmic view of rhythmic structure. You have these smaller pieces of rhythms that happen within a larger expanse of rhythm. And then you come to realize that when you start to talk about the measures of the music, the measures of the quantities of the rhythmic structure, you realize that, well, that's what we're talking about. We're talking about structure. So when I when I look at a distributed system, and I like to think about the data, I like to think about internalizing the data. And that's something that musicians do. It's something that composers do. It's something that jazz musicians do. They learn scales, they learn rhythms, they learn beats. They become aware of the inherent value of the piece that they're either improvising or writing, composing, playing with other people. Those measures and the structure are also something that we want to internalize when we're talking about data, when we're talking about distributed systems. Because distributed systems become their own thing. They become their own, I'm not going to say it's intelligent life or anything, but it kind of is. It becomes its own entity. It starts to present its own kind of rhythmic structures. You know, you always hear talk about people saying, you know, code, let the data tell you how to write your code. Don't write your code thinking that you're going to be able to fit whatever data you want to into it. You really have to internalize how the data is working within the system to write your code. And when you do things like that, when you collect all those measures, they lead up to other things. They lead up to visualizations. They lead up to aggregations. And all these types of measures add up to intelligence, and that's where we win, right? That's when we know my distributed system is working okay, or my distributed system looks sick, or, you know, my balance of data is off balance. We don't want things like that. So let me talk just a little bit about OpenX. This is the only OpenX slide you'll see, I promise. This is just to give you some background about what I'm going to talk about. We are an ad exchange, an ad server, and a publisher monetization platform. Kind of a three-pronged approach to the ad space. We have data centers all over the world, in US, Europe, and Asia. And then here's some numbers just to give you an idea of where we're coming from, because we are talking about global distributed systems here. We're talking about globally connected systems, not just a cluster in the US, a cluster in Asia, a cluster in Europe. I'm talking about a cluster that spans the entire globe. It's the whole world. We get data coming in from Japan, from Europe, from each side of the US, in the middle of the US. All this data is coming in together, and it's all going out together. It's all being shared by all of our locations. A couple of trivia facts. You know, we've got our front ends are 400K and above. That's connections per second between all of our data centers. I talked about Hadoop a little bit. We've got over 6 petabytes of Hadoop storage across every cluster we have. Those are our U.S. data centers, by the way. You know, over 5,000 nodes between data centers. You know, we do our own networking. We're not a cloud shop. We have our own data centers. We have our own equipment. We have our own network stacks. And we do it all ourselves. Reporting data, I mentioned a columnar data store called Vertica. We use that to do reporting. Vertica and our Hadoop grids are closely intertwined. Over 133 terabytes of reporting data. And then my favorite subject is REOC. And I'm going to dive a little bit deeper into REOC as a distributed system, because that is one of our biggest globally connected clusters, is our REOC clusters. We've got over 400 nodes in those clusters, and they're everywhere. They're in every single data center. They share information back into the other data centers. We've got 40 billion unique keys between all of those clusters. And it's not just one kind of cluster either. We've got 4 or 5 different clusters that all do different kinds of things. Some of them collect, you know, basic key value stuff that are very simple. The objects are very small. Those are our largest clusters. We don't do very much that's very complicated. But then we have other clusters that that hold metadata types of things. They're indexed, or we use MapReduce methodologies to use the data in those clusters. And those are our smaller clusters. Those clusters tend to have larger objects, tend to have more complex keys. Here's an example of some of our, I've already said some of these things. Cloudera is actually our Hadoop management suite. Vertica I mentioned. On Riak, we cover the whole gamut of what Basho has in the Riak space. We use the Riak Enterprise server version, which gives us that multi-data center replication. It also gives us great support from Basho, but the biggest reason that we buy Enterprise Riak is for multi-data center replication. Multi-data center replication is also available with the enterprise version of Riak CS. If you're not familiar with Riak CS, it is the grow your own S3. It's completely, I would say it's a subset of S3 commands, but it's completely S3 compatible. It doesn't have everything that Amazon offers in terms of the API, but everything you use in the CS API, you can use on the S3 API. So it's very portable. You can tell a developer, go read about Amazon S3. That's how you're going to be able to learn to use our internal cloud. Erlang is a very big part of what we do at OpenX, not only because it is the heart of Riak, but also we use it in great effect for our front end. You saw the 400,000 connections per second. That is with Erlang as the front end of our data centers. Our ingress and egress all goes through Erlang. So I'm going to talk a little bit about Riak, so I can, in case you're not familiar with it. It is a key value store. I've got a couple of figures up here. That star-looking thing over in the corner is kind of an example of what we would do to set up a multi-data center replication with Riak. 5 disparate data centers, all sharing data, all that have the same data in a distributed way, and it's highly available. That's one of the great things about Riak, is that you build these incredibly easily scalable clusters. It is nothing at all to add a node or to take away a node, let nodes fail, let more nodes fail. If you have enough nodes in your cluster, let 5 nodes fail. Riak doesn't really care. That's kind of the point. They approach the cluster as the same type of approach that Erlang approaches coding in just let it die. We don't need to worry about maintaining something. If something goes wrong, let it go wrong and let it die. And then we can rebuild very easily through things like configuration management. I'll talk about that a little bit later too. So as I mentioned, Riak does a lot of different things at OpenX. It basically operates in a very real-time aspect as well. Our Hadoop clusters don't touch real-time stuff at all, really. There's some delays in there, and we allow for those delays. We allow for processing. We allow for compute. That's data that's all destined for other locations, data destined for reporting, for other types of metadata tools that our customers use. But Riak is special in our environment because it is real time. It's there not only to provide highly available, highly scalable clusters, but it's there to be fast. It's there to be fast, hold a lot of data, and be available to all of our front ends in whatever capacity they need the data. The other thing I want to talk about on this slide is the ring, the Riak ring. That's what this cool colored carousel is right here. This is the way that Riak manages data is with these partitions. When you write a key into Riak, it writes copies of that key depending on how many times you want that copy to exist. It'll write copies of that key to each of those partitions, or virtual nodes, they're called in Riak terminology. That way, any one of those three nodes, and there are different physical nodes when they get copied, any one of those physical nodes can die, and Riak can still keep going. It can still look at the two copies. Actually, when a node dies, Riak goes, oh, you know what? I need 3 copies of this data. I'm going to copy that copy somewhere else until that node comes back. That's one of the great things about Riak, and that's why you can say things like, just let 5 nodes die. It's okay. It's all right. You may see a very similar big similarity between a mandala and that Riak ring. Actually, when I first found this mandala picture, and it is actually, you know, when they do the sand sculptures and you're looking down over a mandala, this is an actual sand sculptured mandala. I mean, you can kind of see some of the floor over there if you look hard. But interesting how it has these partitioned rings around it, isn't it? And that matches very well with the Riak philosophy. Evenly distributed, and I shouldn't even say Riak, I should say all distributed systems display this kind of symmetry. It's really important to have your distributed systems be this way because you want to be able to let nodes fail. You want to be able to easily replace things without having to worry about data loss. One of the keys to having a good distributed system is that none of the others rely heavily on any one other part. Just like the mandala, things are arranged so that all aspects of the system are equal. And that's one of the big keys. There's no master in Riak. There's no name node in Riak. There's no job tracker in Riak. Every single Riak node does exactly what every single other Riak node does. Now, there's some handlers, there's some concepts of leaders and those kinds of things, but a leader goes away, Riak goes, leader went away, you're the leader now. It'll pass that responsibility around the nodes. Doesn't matter at all to Riak. A version of the mandala that I like that was kind of developed by this composer named Pauline Oliveros, who pioneered this musical concept of deep listening. And deep listening, she found, doesn't always need to apply to music. It can apply to our everyday lives. And that was her, still is, she's still around, great woman, by the way, she's a friend of mine. She realized that she could actually improve her life by taking the tenets of deep listening in music, applying them to living every day. So she went about this by coming up with this concept of attention and awareness. So this is still a mandala. It's still a circle. As you can see, all parts are even. They're all blue, but they're all even. And we have an outer ring. This outer ring represents awareness. And the inner ring, or dot, it could be a dot or a ring, or even a point, that represents attention. And remember this macro-cosmic thing that John Cage was talking about before. The attention and awareness is a very parallel kind of concept because you're looking at microcosms, you're giving attention to something very specific, and you're looking at macrocosms. You're being aware of what the whole picture is. You're looking at, well, how does this thing that I'm paying attention to really fit into my awareness of the entire system? So I found when I started really getting into distributed systems that these concepts, these musical concepts, they make a lot of sense when you talk about distributed data. I like this little thing, this little like crescendo of client to code to data to partitions to nodes to clusters to worldwide mesh. It's kind of cool because when you're troubleshooting a problem, you're going anywhere along that crescendo, decrescendo of the rhythm of what you're doing. So let's plug this back into computer science, okay? Monitoring, I consider the art. It is an art. It's an art of staying attentive and being aware. And there are a lot of ways to accomplish this. These are the 3 bullet points that I think are really important for monitoring, for being attentive and staying aware and making an art form out of it. Instrumentation, that's so important. Got to instrument everything. OS and application equally. It's great if you can instrument your OS. I can see how much memory I'm using, see how much memory I have free, see how much disk I have left, see how much CPU is being used. But if I don't instrument my application, it's not really worth a lot to me. I can tell, oh, well, it's using a lot of system resources. I don't know why. I want to know why. You need to know why. The next step of that is visualization of what you've instrumented. It's visualization of those data points that you're gathering. Visualization allows you to see things that you couldn't see by just noticing that the system is overloaded. And the next step beyond that is aggregation. So these are all interconnected, but they're each very much separate entities. Once we get down to aggregation, whether they be statistics that we've gathered from instrumentation and visualization, or from logs that we've gathered and we put into a certain type of application that does aggregation for us. It's all important, and I like to point out that people on call and people in the NOC love these things. They want to see the instrumentation being visualized. They want to know what these aggregated numbers mean. They want to be able to see them and respond to them accordingly. I'm going to give a few examples of the tools that we use to accomplish these bullet points. Some of you may be familiar with Nagios. iSinga is the it's not really a spin-off. It is a fork, not associated with Nagios at all. They are their own company. They are their own thing. But it is a fork of the Nagios code. And this is simple. You know, we can see things like port monitoring with iSinga. We can look at application endpoint health with whether it be process monitoring. You know, I've got a Beam process running, or I've got my Java processes are running okay. But it does have some nice visualization too. You can get cool history and histograms. It's kind of where iSinga stops, though. You don't get much past that. It's very much applicable to the single node as well. You can't get a lot of clustered health when you look at iSinga and Nagios. So one of the things that we use to instrument our applications and OS is MonDemand. MonDemand may not be something that everyone is familiar with. This is not something that's highly used, but it is out there. I believe it's in GitHub. You can search for MonDemand in GitHub and find a bunch of different libraries and the server-side stuff, different clients that you can use. But we use it because we love plugging it into Erlang. As I mentioned before, Erlang is a huge part of what we do at OpenX. Java actually is as well. JavaScript is actually also something we use a lot of. But Erlang and Java are really where MonDemand shines. And that's where we're able to aggregate data. That's how we're able to, build on-demand graphs of the things that we're looking at. MonDemand can use backends, several different backends. RRD is how we use it. We also use it with Remon. I've been putting MonDemand stuff into Graphite as well. It can emit into OpenTSDB, and that last one, Quora, that's an in-house thing that we wrote that is actually kind of an extension of MonDemand itself. Excuse me. So some of the images you'll see coming up are actually Quora aggregations of MonDemand stats. In fact, there's one right now. Kind of a pretty picture, some stack graphs. Those are always fun. But I have these broken out. These are actually representative. This is a single Riak cluster in one of our data centers. This is representative of all the different kinds of statistics that you can get out of Riak. You can see how well we're measuring things, and we're getting a lot of cool rhythms. This is what I refer to as a data rhythm, these waveforms. you internalize what these happen. You know that you'll get a certain kind of peak and valley that goes with your front-end traffic, for example. Or you may not get stuff that really follows a traffic pattern. You may get stuff that's more like, regular memory allocation, ongoing memory usage, things like that. You can get all kinds of cool percentile measurements in Riak, which is very, very useful to troubleshooting and actually learning about how your clusters are operating and how they're existing. Here's another on-demand Quora example, kind of a jumble of stuff, but just to show you different types of displays of the data. Here's a good example of the rhythm going wacky, this spike right here, or even this right here. This is over a year. I forget what cluster this is with, but at some point here in June or almost July, the rhythmic structure of that data drastically changed. So something happened here which made it go, oh, the latency just bumped way up. Now it's interesting because it has a similar type of feel to it, but it definitely, the levels boosted way up there. I think that had a lot to do with the object sizes, and that's why this other object, get objects graph is here, which is kind of interesting actually, because you get to notice, you kind of see this jump, but this jump doesn't match that jump. So those are the kinds of things that you notice when you are able to internalize your data, and when you look at your graphs every day, and when you kind of like feel your way through the rhythm of what the data's doing. Things like that happen, and you notice it immediately. And that's a big win when you're in operations, because you can tune in and hone in on those events, and then try to search for other things that you can correlate. Visibility, visualization. Here we go, more visualization. Now, on-demand in and of itself is a good visualizer. Munin is as well. Munin doesn't do so great at aggregation, but when you really need to dig down deeply into what's going on with your nodes and your clusters, Munin's a really good thing. It gathers system statistics. What we're looking at here is memory usage. This is a particular problem that we ran into with our Riak clusters. And by noticing this rhythm of the data, this crescendo here, that scared us a little bit. Because we're like, what is going on with these zigzags? It was fine for a while, but then at some point, this sawtooth pattern started creeping in. And it creeped in so far that it made Erlang and Riak crash. There's a different example of that same pattern. But the reason that I wanted to show this is because Basho, the company that makes Riak, loved that we had these graphs. They loved the fact that we aggregate our Riak statistics and that we're able to provide, digging deep down into the memory profiles of each node. A lot of nodes, actually almost all the nodes in this cluster were doing this. So they were able to take, my personal anecdotes to them, which they can believe or not, but then I can show them these graphs and go, here's what I mean. You can see it right here. And, they love that because they can use that. And we actually solved the problem, and we had a bug fix put in, and we were able to help Basho, stamp out this particular bug. And we help them in that way all the time. And each time that we help them in this way, we have a very close working relationship because we're able to give them the statistics and the graphing that they need to be able to help us and help other people that are using Riak. If you're interested in the technical details of what's going on here, this drop here at the end is where we turned off the merge worker and the garbage collection was able to proceed. And instead of Erlang trying to reallocate more and more memory each time because of merging, when in React that's also known as compaction. Bitcask is a backend that allows you to just add data to the end of a file. So when you add data to the end of that file, it has to be merged. It has to be compacted every once in a while. That's what this memory profile is showing. It's showing how it's not really a memory leak. It's actually Erlang and React not being able to keep up with that 40 billion key count. That has a lot to do with it. This doesn't just happen in React. This happens because we have billions of keys in React, and because we're expiring things all the time. This is actually user data that I'm talking about here. So it expires and refreshes itself daily and all day long. So it's a big problem when we start getting memory problems like this. Next after visualization was aggregation. And one of the, obviously, the Quora aggregation we use with MonDemand a lot, but one of the other aggregation tools that we use is Sumo Logic. Sumo Logic is a, I guess it's a cloud application. It's a cloud-based tool. If you're familiar with Splunk, it's very much like Splunk. Splunk is obviously an in-house tool. You have to hire 3 people to manage it, that kind of thing. Sumo Logic is a way to be able to have Splunk-like functionality, not have to burn an entire SRE just to manage your Splunk stack. And it has a lot of different ways that data can get into it. We use our syslog. And our syslog is the reason for using our syslog in this case is because I can tell our syslog, I want you to tail these files. We can do syslog stuff, and React is cool because it has this neat thing called logger. Actually, Erlang has logger. Logger, and that is lager like the beer, lager, and sounds like logger. It's a direct-to-sys log type of thing. You can configure, it's nice because I can configure logger to write to files at the same time that it's writing the syslog. So I can just tell it, write the syslog, our syslog, forward those messages on the Sumo Logic collectors, and then let's send it all up to Sumo Logic where we can start aggregating the data. The search engine is very robust. I should say the search language. It's Java regex. It's not all regex, though. It has some quirks, some kind of different capabilities depending on what pieces of the data you want to look at any one time. For example, you can see a query right up here. This is a query, again, in a React cluster, looking at large objects. Oh, yeah, I saw some problems with large objects before. That's interesting. Well, I'm going to get into my Sumo Logic aggregator, and wow, look at these. These are big. These are 50 megabyte objects. That's huge for a key value store. 50 megs is gigantic for a key value store. In fact, Basha recommends not to even go above 5 megs. So in this particular case, I swear we went for weeks, months even, not knowing what was going on with these clusters. Why was multi-data center replication failing? Why were all these nodes continuously rebooting themselves? Well, we finally found out by putting log aggregation together, by getting, it was, over 24 different nodes. We get all those logs together, and then we can see, oh, like every minute almost, we're getting these large objects being operated on. Well, that was it. That was the answer. Don't use large objects. Bing, talk over. Just kidding.
So
yeah.
Is this dashboard layout something that's part of a tool that you're using right now, or is this something that...
This is the Sumo Logic application itself, yeah.
Okay.
Yep. So this one down here is actually not related to this, but I wanted to show it because it's a cool picture. This is actually a picture, a screenshot of our front-end UI which is not our gateway. That's not actually part of that 400,000 peak connections per second. This is the UI that our publishers and our advertisers use to come in and configure their stuff. So I can see actually with Sumo, I can visualize where they're coming from. I can do things like look at, I think this might be a error code graph. One of those is an error code. I think this is a connections versus bandwidth. That little green line is throughput. The yellow bars are connections. And I think these are only set at like 3 hour. But you could do like these at 6 hours. Or you could have these display, and they do continuously reload for 12 hours if you wanted to. And it'll just sit there and add the data and aggregate it and show you this aggregated version of your data and what you're looking for. Really, really helpful to immediately correlate events. I can look back at those other graphs, the Mun and the on-demand graphs, see these events that are interrupting my nice, free-flowing, rhythmic structure of my data, and start correlating what is happening, what actually is going on underneath the hood. That's what all this helps us do. But one of the things that's really important to doing this is homogeneity. We cannot have good visualization, we cannot have a good distributed system, and we cannot have a reliably trustable distributed system if we don't have homogeneity. And I like to think about this, it has to be as easy to replace the nodes as it is to have to let them fail. Again, let it die. Let them fail. Let them die. Let a node drop out of the cluster. It's not a big deal. I don't want to be woken up about this. It's gonna be fine. Even 3 nodes go down in the middle of the night, the NOC will go, oh, okay, acknowledge. We'll tell you next morning what's going on. The way that we're able to trust this is by managing configurations. Configuration management, right? How do we guarantee that our cluster is exactly what we know our cluster to be? We build an architectural structure. So 2 different kinds of structures, right? We've got a rhythmic structure of the data, which shows things like, micro, macrocosmic fluctuations of crescendo and decrescendo, of what our data is doing, of icti and events that happen that we have no idea what's going on. We build architectural structure to help us figure that stuff out, help us interpret what's going on. So John Cage, that piece that we talked about earlier, those measures that we saw at the beginning, they're from a piece called Sonatas and Interludes for Prepared Piano. And what John Cage did is he took these little pieces of rubber and screws and washers, and he stuck them in between the strings on the piano. And so when you hit a key on the piano, you didn't hear a piano note. You heard this. That would be, the screw is in the middle of those strings, causing a completely different kind of sound. And that's what John Cage was going for. But the cool thing about what John Cage wanted to do is he didn't want to just do this in an improvisatory manner. He wanted to build this as a piece that other people could also compose, that other people could also prepare a piano and perform the piece. And that's what all this is, table of preparations. This is John Cage's configuration management. He's telling us what note on the piano gets what kind of object. You see screw, rubber, 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 screw. He gets pretty specific. Different kinds of, oh, here we go, furniture bolt, medium bolt, medium bolts. He probably had a big pile of stuff, He's like, okay, there's a large bolt, medium bolt, furniture screw, whatever. But we do the same thing. We do the same thing in computing because we want it to be repeatable. That's one of the biggest points behind good configuration management is repeatable stuff. It's easy for me to let a node die because I know I can consistently, repeatably, and trustworthily, is that a word? Know that I can rebuild another node and slice it right into the middle where the other one failed. And that's where Salt Stack comes in. Sorry I didn't put a Salt logo at the beginning. I was kind of tried to surprise you. But configure intelligently, repeatably, and elegantly so that it becomes out of mind. It's almost out of mind, out of sight. Yeah, we know, oh, node failed. We need to go back in. But all I'm going to do is hit the deploy button. I'm not going to go into Salt and go, hey, I need to do this, this, and this, and this. If you have your table of preparations laid out good, just like this, the operator doesn't really have to think about it. You know, the piano's been prepared. All you have to do is play it. And that's where good structure management and orchestration with things like Salt come into play. The rhythmic structure of the data. It's supported by the architectural structure. They go hand in hand. Again, back to you let the data tell you how to code. You let the rhythmic structure of your data help you decide, or maybe make informed decisions on, I should say, how you're going to structure your application, how you're going to structure your code, or how you're going to architect your clusters. And architect is a great word because that's exactly what we do. We're not looking at, oh, you know, boom, we just have a little cluster over here. You have to think about where on the network is that cluster? What other clusters did I put this on beside? Are there other clusters that need the same resources of this cluster that I just built? Is this cluster going to have to talk to Japan? Do I need to put this data a little bit closer to Japan so that I get those little extra milliseconds of latency burned away? Those kinds of things make you think about how you're going to design it. But then, you know, you get down to the rhythmic structure of the data, and it's not really flowing in the way that you think it should flow, or the way that you want it to flow. So you go back and revise your architecture. This is kind of an example. This is a tree view of a Salt configuration. This is actually a Reox CS config. Now, our Reox CS clusters span every single data center that we have. It's 5 data centers all over the world. And in each one of the 5 data centers, they all get built exactly the same. I did this once. You know, this shows some simplified examples here of what Salt refers to as an SLS file. But it gives you ways of managing different things. You can include different types of files. These other includes up here are actually other SLS files. You can kind of see those over here. You can use templating in Salt. Jinja is the template that we use. And that's why you see these .jinja2 extensions over here on the app config and VM ARG config for Reox. And then a lot of the Reox CS pieces are nice to be able to kind of orchestrate, because with Reox CS, you know, it's similar to something like Storm. If you're familiar with Storm, there is a supervisor in Storm. The Nimbus node is known as a supervisor in Storm. In Reox CS, we have a stanchion node, which is very similar in operation and in what it does in the cluster, but you can only have one. So I actually use Salt to orchestrate to the cluster which one that is worldwide. So this configuration, this entire management, this configuration management, this architecture is repeatable to every single data center. We open a data center in Belize tomorrow, bam, it's there. I can, yeah, Belize, let's do it. You know, this takes, I always joke, someone comes up to me and says, I need a Reox cluster. How long would it take? 10 minutes. You got it, 10 minutes. That's a little bit maybe unreal, but in many senses it's not. It does take a little bit longer to go, oh, well, I do have to provision hardware. I do have to set up some networking. I do have to like build some VIPs and that kind of stuff. But then I hit deploy and it's all done. And you know, that's basically 10 minutes, right? So in the last couple minutes here, I want to go through kind of a case study of what I was talking about with, well, kind of like, let's put everything I talked about together here. Rhythmic structure, measuring what we've got. We've got instrumentation, we've got visualization, we've got aggregation, logs, we've got configuration management. Okay, Matt, that's cool. How does that help you? Can you show me how? I can show you. I definitely can. What are those spikes? Everyone asks this question. I bet anyone who's a sysadmin in here has asked that question at least every day, if not multiple times a day. So, internalizing rhythmic structure, right? That's what we did here. When I look at React graphs every day, I love seeing nice, good, these aren't exactly nice, good sine waves, but you get the idea. This is a breakout of the put times in a particular React cluster. This is the healthy one. Probably the most important one over here is the mean. That is mean, right? Yep, that's mean. And you get 95th, 99th, 100th, but you see how the mean's nice and smooth. Kind of smooth. But then look at the numbers. Good. That is 3K, 2.1K is the peak, 21K there, and these are microseconds of latency. Not the case here. We don't even get a sine wave right there. It's hidden. It's like you can kind of tell here, but yeah, it's not there. I've got these gigantic peaks. I've got what I need to be microsecond latency is getting up into the millisecond area. 1.5 million microseconds. Not great. That's the 99th percentile. But even down here at our mean, we're talking about 100,000 microseconds. That's not good. We want stuff like this. We want like dozens of microseconds, not hundreds of thousands of microseconds. So this is the job that we have to do. We have to figure out what these spikes are doing. And when I first noticed this, I was looking at graphs, because I look at these graphs all the time, and you should. If you're a sysadmin, even if you're a developer, look at the graphs. Just take a minute. You get to work, sit down at your desk, pull up some graphs, get your coffee, look at the rhythmic structure of your data. I guarantee you that will help you in your everyday job, hands down. Because when you're used to seeing this, and then you see this, even if it's out of the corner of your eye, you're like, what? And you start asking yourself questions. What's going on there? And then, a couple of weeks go by, and Dev sends you an email, hey, we're getting a lot of errors from our application. What's going on? I don't know. I'm going to go look into this. So I'm going to go look at all the nodes. I'm going to go look at all the individual nodes. Are nodes failing? Is stuff going wrong? Every time these spikes would happen, we would see React start to hand off partitions. I mentioned earlier how when a node fails in React goes, what were you doing? Okay, I'm going to make someone else do that now. You can be failed. It's cool. You can be failed for a week for all I care. It doesn't matter. I'm going to hand off all the partitions that you were using. And that's what all these handoffs are. So as I was troubleshooting this issue, looking at the graphs, looking at individual nodes, trying to figure out, oh my God, and I couldn't do it. I couldn't figure it out. I would come into nodes that would be like, okay, there's some disk problems. Oh, okay, this node's got ECC errors. All right, memory stuff is going on. So address some of those problems, and these spikes didn't go away. Until one day, I was looking at React doing this. It was not during a spike, so I didn't get this part up here where it says nodes are currently down. I was just looking at the handoffs. But then all of a sudden, I happened to have one graph up, and I happened to have this terminal up, and I saw the spike on the graph go, and then React said, hey dude, you got 5 nodes down. And that was a hint to me. 5 nodes going down at exactly the same time? That can't be a node problem. That cannot be a problem with the application. It can't be a problem with my configuration management. I mean, 5 nodes having a different configuration, that doesn't make sense either. So that's the thing that made me think, I need to broaden my view. I need to look at some other aggregates. And that's when I looked at cacti. Cacti is a network version of all the aggregation that we did earlier. Now, cacti doesn't do the same kinds of application level aggregation that I really want or really need, but it gives me a great picture of the network. So before, all I was looking at was this. I was saying, oh my God, this is protobuf connections. Connects and active connections, what is going on? They should be down here. They should actually look like a sine wave because those protobuf puts, the connections themselves, they follow traffic. This isn't a data warehouse. It follows traffic. It's real time. This is not real time. This is not, it is, but it certainly doesn't look like it. But then you see what I started noticing? See that peak? See that peak? These peaks match up exactly. And it was the aha moment. I'm not kidding. It was 2 months of troubleshooting this issue before that I happened to see that Riak ejected 5 nodes. And in distributed systems parlance, that's known as network partition. Now, this is really cool because it illustrates how good Riak is at suffering through network partitions. When these network partitions happen, and that's what each of these spikes are. These are all network partitions. Each time each one of these spikes shows up, you could go back and look at that terminal screen and you'd see Riak go, bam, 5 nodes went down. Bam, 3 nodes went down. And they were all different nodes. They were different groups of nodes. So I'm like, what is going on? So what we learned and what I discovered was that these are Hadoop nodes. These are Hadoop nodes, and whether or not it was a fault of not architecting it right, or just scalability, or whether it was just like something that we couldn't have foreseen. We may not have known this was going to happen, and that happens a lot. You don't know everything. You can't. You can try to plan for it, you can try to architect your structure for it, but you can't know everything. So what's actually happening here is we have a grid of Hadoop nodes that do high compute tasks, and a lot of them, and big ones, big long ones. And compute tasks in Hadoop are distributed like this. You're always going to see the same kind of network patterns on Hadoop nodes, on each Hadoop node that you see on each of the other Hadoop nodes that are doing the computation. It's always going to look the same. It's distributed. So that's when I figured, oh, there's 12 Riak nodes in this rack, and there's 30 Hadoop nodes in this rack. No wonder. Those Hadoop nodes were saturating the switch. And Riak was going, oh, okay, they're back. And when they came back, Riak is awesome at going, okay, all those handoffs that you lost because that network partition happened, they're back again. I wrote them to some other nodes, and because I'm able to do comparison and correlation between the keys, I can do read repair on those keys, or I can do what they call active anti-entropy, and do the key repair in the background. But whatever way that the key repair gets done, Riak weathers the network partition, and it's all fine. In fact, it's fine to the point where, because of the nature of this application, we don't care about it so much. We're going to get that data right again when we get that brand new data every day. This is the same data that we get every day. So if we lose that data for one little thing, and even in the next few minutes, that data could be refreshed by what we call pixel drops. That's another talk. So by using all this aggregation, I was able to find the culprit, able to locate the exact nodes that were causing this. It's not the whole Riak cluster that's affected, by the way. It's just maybe like 2/3 of it that were affected. So we're addressing this issue by making sure that our network fabric is updated to the point where, okay, yeah, it's not a good idea to co-locate two extremely important and busy distributed systems on the same network hardware. Okay, granted, yes, that's true. But we can also try to mitigate that kind of limitation by giving us more network overhead. So that's how we're solving this problem. Again, right back to those points, bullet points that talk about measurement, talk about measure. The instrumentation, it was at the right places. It allowed me to collect the data that I needed. The visualization of that data helped me locate those events, helped me do the correlation, helped me, even though at first I didn't readily see what was going on, paying attention to it and being aware of the rhythmic structure of the data helped me know where to look. And that's what's important. And the homogenization, of course, of configuration management. It allowed me in there was actually another cluster that was affected by this that I was able to use configuration management to quickly fix. Get those nodes out of there and put them somewhere else. Took 10 minutes, right? It did. So lesson learned, don't let your elephant beat up your ninjas. And that's it.
Questions?
Thank you.
Questions? Raise your hand, please.
Yeah, I am. I emailed them to whoever is, responsible with that. So wherever the SCaLE slides show up online, it'll be there. Yep.
Yeah, just keep an eye on the website and the blog, and we'll get it to you.
Cool.
Are you a musician by any chance?
Yes. Huh?
You are.
Yeah, I am. Yep. That's, people always ask me, because I went to music school, I didn't go to computer science school. I actually failed my only computer science class. But people always ask me that, like, you went to music, like, how are you doing this? How are you into computing? How are you doing distributed systems? And I'm like, well, this is why. It's very similar. I mean, it's so similar that I use a lot of my musical knowledge and my musical training to help me figure out what's going on in the data.
A lot of technologists are musicians. The brains work the same way.
Yeah, that's true.
Further questions? All right, so I wanted to let you guys know we have the expo floor open till 2. So if you'd like to go check out SUSE, please do so. They are our sponsor. The reason we're able to make this event for such great prices is thanks to our sponsorships. So the next